So first, to start off, maybe some of you are not familiar with a Rust programming language. It was released in 2015, and it's very popular because it was voted the most loved language since then on Stack Overflow, according to Stack Overflow. And its characteristic is that it's fast, but at the same time, it's safe. It's as fast as C or C++, theoretically. In practice, also as well, often, but not always. But theoretically, it's as fast as C and C++, because it has no garbage collector, and you don't pay any runtime cost if you're not making it explicit. But it's also safe, contrary to C and C++, because you don't have any undefined behavior. And as I wrote at the bottom, around half of the Linux kernel CVEs from the beginning of this year until April would have been avoided if the kernel was in Rust. But of course, we are not advocating for this, but just so you know.
Rewrite it in Rust?
Exactly, rewrite in Rust. Libp2p is based on the Tokyo library, which is an asynchronous eventing library. You can check it out at tokyo.rs. I'll put some benchmarks at the bottom. This is, I don't remember the name of the website, but it's benchmarking HTTP requests. And it's pretty fast. It's this Tokyo mini HTTP project demo is 2nd and 7th on 2 different benchmarks. It's not in any other benchmark, but in the 2 it's competing in, it's pretty fast. And it works similarly to Node.js, which means that whenever you receive an event, the thread wakes up, processes the event, and then goes back to sleep if there's nothing more to process, except that we can do this in a multi-threaded fashion, contrary to Node, which is single-threaded. And another fun fact about Rust, you can compile for ASM.js and WebAssembly. So of course, if you do this, you don't have threads or a file system or anything like this, but you can compile it. The same piece of code that compiles on a desktop can also be compiled and be run on the web, provided you don't use threads and file system and so on and so forth. And Parity and Polkadot, which are 2 projects I'm working on, we plan on compiling them for the browser so that you can run them on a browser. A small disclaimer. Cryptographic libraries used inline assembly, and that doesn't compile for the web, obviously. So we have to solve this problem before making it real. And this talk is about the Rust implementation of Libp2p. Otherwise, my slides would have been quite off topic. It uses Tokyo, designed to have as few overhead as possible. And one important thing is that when it comes to the API, I've designed it on a bottom-to-top fashion, which means that I first tried to write the most low-level code and expose this, and then build on top of it, on top of it, on top of it. I didn't take the opposite approach with this top-to-bottom, which would mean I designed the high-level API first and implement it underneath. I didn't do this. I did the opposite, first implementing the low-level, and then the high-level on top of it. The reason why I did this is so that I'm sure to have maximal performances and not pay any cost because the API is badly designed. And so that means that unfortunately the high-level API is still work in progress, but yeah, a lot of parts are already more or less stable. More or less stable means it's stable, but we reserve the rights to make modifications. So you can use it, but it may break slightly. And so here we go. This is an actual introduction to the Rust code. So if you've never seen Rust before, this is what it looks like. So I'm going to show you how to use Rust Libp2p. So first of all, you have this concept of a transport that also exists in Rust Libp2p, which is on the form of a trait. So a trait is similar to an interface in Go, for example. It's implemented on types such on configuration types, TCP IP config, WebSockets config, DNS config, and so on and so forth. You also have like relay config and things like this. Unix config, Bluetooth config, whatever you want. And how you use it, you build this configuration object, and then you call dial on listen on. So first of all, we create a Tokyo core, which is the event loop of Tokyo. We create a configuration based on this core, and then we dial an address. We dial IPv4 IP port 13303. And so that's pretty low level. That's not easy to use. That's the lowest level layer. You can combine multiple transports into one. In this example, we create a TCP transport and a WebSocket transport, and we combine them into one at the last line, and into finite transport. And so when we dial finite transport, it first tries TCP. If TCP doesn't accept the multi-address, then it tries WebSocket. So for example, if you try to dial an address that ends in /WS, it's going to try TCP. TCP says, I don't support WebSockets, sorry. So it's going to try WebSockets, and WebSockets will succeed. Then on top of a transport, you have another thread, which is connection upgrade, and that allows you to upgrade a transport. So upgrade means upgrade to Sekayo or Mplex or Yamux or whatever you want, or any custom transport or any custom protocol, that you decide. So I showed an example. First we create a private key, and then we create again a Sekayo config object with this private key, and we upgrade the transport with the config we just created in order to obtain a with Sekayo layer, and with Sekayo layer also implements the transport thread, which means that you can use it exactly the same as the previous transport. If you look at the bottom code, it's exactly the same code, except that I changed the IP. No, I didn't change the IP. It's exactly the same code, except that this time, when you dial, it's going to upgrade to Sekayo first, on top of TCP or WebSockets. Step 3. We can combine multiple transports and multiple upgrades. So I showed this on the example. We create a TCP config, a WebSocket config. We merge them into one. On top of it, we put Sekayo, and on top of it, we put Yamux. Yamux is something we just merged into the repository a few days ago, so I'm not sure it works, but you can use it. I mean, it works according to what we tried, but we haven't tried it in any real example. And so we combine everything into a base transport, which is here. I didn't really explain the rest code, so I hope you can follow. We merge this into a base transport, which will serve as the base for everything we're going to build on top. So every single connection we open, we receive, and so on and so forth, is going to be TCP or WebSocket, then upgrade to Sekayo, then upgrade to Yamux. And this whole API is zero cost. So, I mean, theoretically there are some minor costs, but there's no memory allocation or anything like this. I mean, when we create the key, there's a memory allocation, but there's no unnecessary memory allocation. There's no garbage collecting, and so on and so forth. Step 4, this is how we create a custom protocol. So if you're familiar with a JS Libp2p repo, there's an echo example, and this is the same here. So normally, if you want to create a custom protocol, you create a custom struct that you name, for example, foo config, if your protocol is named foo, and you implement a connection upgrade thread on this foo config, and then you can use with upgrade, like here, exactly the same as in Sekayo and Yamux, but with foo config. You can use it exactly the same way. But if you want to quickly prototype, as in this example, because implementing the connection upgrade thread is quite long when it comes to code, if you want to do this in a simple way, you can just create a simple protocol which implements connection upgrade, and that's much shorter. So what happens? This is the name of a protocol that is negotiated with multi-stream select. And whenever we successfully negotiate echo, we enter this closure. That's a closure. That's a function. We enter this closure with the socket, and we return whatever we want. So here it's, I didn't explain this line of code, but basically means that we are adding a length at the beginning of each packet so that it's correctly delimited. This is how we use it. So exactly the same as I showed before. You use your transport, you call with upgrade, and you obtain a transport that automatically upgrades to Sekayo, then Yamux, then Echo. And so you can use it to dial the third line of code. We dial this IP address. And as I said, it automatically upgrades. And once we've successfully upgraded, we enter this closure here. That's a function as well. And sync stream is what we return. Oops. Hey. Sync stream is what we return at the bottom. This frame due, blah, 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 is put into sync stream. And we can do whatever we want with it. In this example, I sent hello world. So you may be wondering, what is this map thing? That's an unfortunate consequence of Tokyo. It's a bit hard to use. It's not very intuitive. Basically, when you call send, it returns the sync stream object. So when you call send, it takes ownership of a sync stream, and then it calls the closure path to map with a sync stream object back so that you can use it again. It's a bit complicated. It's the consequence of being zero cost, unfortunately. There are a lot of critics about Tokyo being difficult to use, and I agree with that, but in the future it's going to improve a lot by additions to the Rust language. And so, yeah, one thing I put in this slide as well. So we do this whole thing with upgrade, we dial, and then we send hello world, and that's put into a variable named finished. Let finished, that's a variable. And it implements a thread named future, and in order to make this work, we have to call core.run finished. Core is the Tokyo event loop that we created at the very beginning. Sorry. It's a consequence also of using Tokyo. So far we've just been dialing or listening manually. I didn't show any example of listening to incoming connections, but it's quite straightforward. So far we've done everything manually, but of course in a real code you don't want to do this manually. So there's this thing named swarm. So this code shows how to use it. We have a function named swarm that's in Rust Libp2p. We pass whatever we want to happen. So we take our transport and the echo protocol. And whenever we negotiate a connection with any remote peer, we enter this closure here. And we choose whatever we want to do. Whenever we successfully negotiate a connection. So that builds a swarm. And then you can control the swarm by using the swarm controller. So here we listen on this address here. And so this passively listens to incoming connections, and whenever a connection arrives, we enter the closure that's on the top, and we send hello world. And again, you have to run the swarm future for things to work. But this code is like a complete example of Rust Libp2p. We just create a swarm, we make it listen on an IP address, and then it runs forever and listens to incoming connections. And again, this is zero cost. Theoretically, more like no unneeded runtime cost. The reason why we designed it this way, so that you have this swarm, is that you have a single entry point for every single connection you negotiate with a dialer or a listener, and this makes things very easy to debug. So note how the user of a library has a complete control of everything that happens once something has been negotiated. So you can do anything you want. You can log this. You can use it for statistics and so on and so forth. For example, if you want to have statistics about the number of connections, you can just tweak this closure, and you don't have to modify Rust Libp2p itself. And then once you have your swarm controller, you can pass it all around your code. And that's the single entry point for when you want to dial or listen with the swarm controller. Next step is setting up Kademlia. So first of all, in this code, we just listened to a single protocol, which is echo. But with Kademlia, we want to support both echo and Kademlia. So this is a bit hard to read if you're not familiar with Rust, but this is basically an enumeration. So this can be either echo of Kademlia or Kademlia, sorry. We build a single implementation of connection upgrade that merges both echo and Kademlia. This is our upgrade.map is like administrative so that it creates the correct type, otherwise you get compilation errors. So we merge both into a listening upgrade, connection upgrade. That's a mistake in my code. That should have been base transport dot with upgrade listening upgrade. But that doesn't work. You should upgrade the transport with it first. And then whenever we receive an incoming connection, it tries to negotiate either echo or Kademlia, and again, it enters this closure here, whose command is going to be on the next slide. And then again, you can use the Swarm controller to dial. Note that when you dial a remote, you have to choose yourself between echo and Kademlia, so we have to recreate the transport. But whenever you dial, that jumps here as well. That's the single entry point for everything. And this is the content of the closure. So whenever we negotiate, we enter here. And if we receive echo, we send hello world. If we receive Kademlia, we dispatch to a function named handle Kademlia. So if you combine this and this, it's still pretty short, I think. It's still quite readable if you're familiar with Rust, but you have zero overhead and total control over everything that happens. That was the premise of the library. And this is the handle Kademlia function. Sorry. So again, you have total control over everything that happens. Every single request that comes from the remote are dispatched here. If the remote requests a find node, we respond with a responder that is provided. And if it's just pinging, then we do nothing. Normally, you have to upgrade the K buckets, but I didn't show it in this example because it would be a bit annoying to write, but it's also very brief. And again, this is on purpose. I'm repeating it myself, but this is all on purpose. The fact that you have total control so that you don't have any overhead and you can do whatever you want. You can have, for example, multiple DHTs very easily just by tweaking the code without having to modify Rust Libp2p. You can refuse peers if they are malicious. That's something that we are going to do in Polkadot. If a peer happens to do something weird, then we just cut it totally. And if it tries to dial again, we just refuse it. And this is something we can do thanks to the fact that you have total control. So far, Kademia has only received, we only handled Kademlia for incoming connections, but we also want to perform queries ourselves. So for this, we create a Kademia system. We pass some configuration, the timeouts, the bootstrap nodes, so that it knows what to dial first. We have to create a Pierre store, obviously, in order to handle requests. This is something I didn't show here, but the build.cad response is a function that also uses a Pierre store in order to build a response for an incoming Kademia request. And in order to perform a peer discovery with Kademia queries, we do this semi-manually. So you have to do everything manually, but you can use helper functions. So we build an interval which will automatically perform an action every 300 seconds. And we perform a find node iterative query. And again, every single event that happens during this find node is handled by this closure. So when we learn an address of a peer by receiver response, it's dispatched in this closure, and we can do whatever we want. We can log it. We can put it in the peer store, which is what you are supposed to do. I didn't show it here. But you are supposed to add it in the peer store yourself. Again, that's one line of code. And when it's finished, reproduce the output, which is here, and you can do whatever you want with the output. Whatever you want, meaning dial over nodes that you receive. And so that was an example with Kademia, just to show you the idea of a library, B0 overhead, basically. But this works the same for every single other protocol that you may wish to use. Float sub works the same. Gossip sub, it's not implemented, but it would work the same. If you create your own protocol, it would work the same. Which means the user decides which peers to connect to. That's not automatic. You have to call swarm controller.dial, but again, that's one line of code. And every single time you successfully negotiate a protocol, it enters the closure of a swarm. And and the closure of a swarm should receive some sort of controller that you can use to control your protocol. And if you put everything together, so just to summarize everything, you have a base transport that you create manually with TCP, WebSocket, SecIO, Yamux, everything plugged into one base transport. You create implementation of a connection upgrade thread for all your custom protocol, or you use the ones that already exist, like float sub or ping or Kademlia. You merge all your upgrades together and you pass this to the swarm, and that's what your server is going to handle. And you create a peer store, a CAD system, and you handle Kademia requests, and you perform Kademia requests thanks to this Kademia system that you create, thanks to the peer store. And you use the result of your Kademia queries in order to dial nodes. And I think that's it. I think I'm on time. And now questions, I suppose?
Yeah. So when you compile it to WebAssembly, are there any issues for like maintaining the threads, the number of peers you can connect to?
So far we haven't tried with WebAssembly. We have tried with ASM.js, and apparently it works fine. We haven't had any real issue. The issue is you cannot use SecIO because of this crypto library thing in assembly. But other than that, it seems to work fine. So
I suppose you could assemble it. I'm thinking for like WebSockets within the browser, to actually compile it to WebAssembly, use a JS crypto library, maintain keys in session stores or local storage, and then handle the crypto.
Yeah, so the problem is that the JS crypto API is asynchronous, while like whenever we want to do something cryptographic, we just do it on the CPU, and the JS doesn't do that. It creates a query, and then you obtain the result later, and so plugging it into the code is kind of complicated.
How many nodes have you tested it with? Like spin up thousands of peers and just connect them to each other?
No, so I'm just testing with 3. That's very low.
Rust is fast.
Sorry?
Rust is fast. You should spin up hundreds of thousands.
Yeah, but we are going to try this at some point. Like, we are going to merge pretty soon the Libp2p switch into Polkadot, and then we're going to test. It's going to be in proof of concept 2 with users using it. So it's going to be a very good way to try if everything works.
This is awesome. As far as I understand it, you're like the first one to write a Libp2p implementation in a new language. How was that experience?
So we've often been complaining about the lack of specifications. We had to read the JS and Go code in order to understand what it's doing. This has been a bit complicated by the fact that the JS and Go code are a bit, they have like some relicates at some places, like obsolete code. And we thought it was used, and we mimicked the code, and it turned out it's not the way it actually works. But it turned out fine, so.
It would help a lot if you could help us, like by opening issues on the specs repo, like if it's still fresh in your mind about what things were confusing. So I just put that out there.
Yeah,
But
that's true.
I know you have a lot of other work to do, but it would be a huge help to the project. But.
I mean, at this point, it would probably be the best idea to just write the specs instead of opening issues about what's missing, because that's much easier now.
Do you have a vision for what like a higher level API would look like in Rust?
So, like right now, I've been implementing Libp2p in Polkadot, and that's a concrete real-world example. And so what I'm going to do in the follow-up weeks, I guess, is try to make the Polkadot code simple, extract things from a Polkadot code in order to put it in Rust Libp2p, so that any user of Rust Libp2p would have a very easy experience.
Cool.
Okay, I think we're going to wrap it up there and move on to the next talk. So thank you.